Recent events have rekindled interest in the vast expanse of our solar system. For a long time, it was believed that its structure had been fully studied, with only details left for scientists to clarify. But is everything really that obvious? Some data suggest that we may have overlooked something important over years of observation. New hypotheses about possible objects on the periphery of the solar system continue to intrigue researchers. Attention is being drawn to phenomena that do not fit into conventional models. Is it possible that somewhere out there, in the distant cold space, something entirely unexpected is lurking? The year 2024 has seen significant breakthroughs in certain areas of science. But how much do these discoveries have the potential to change our understanding of the universe? And what else is waiting to be discovered? The latest breakthroughs suggest we may have only scratched the surface. Liking this video helps us share these discoveries with more curious minds, and subscribing ensures you'll never miss a chance to explore the universe's secrets alongside us. Let's journey through the stars together. The solar system is a planetary system that includes the central star, the sun, and all natural celestial objects orbiting it. It formed about 4.57 billion years ago through the gravitational collapse of a gas and dust cloud. The solar system officially recognizes 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. However, in recent years, astronomers have proposed a hypothesis about the existence of a 9th planet, unofficially referred to as Planet 9, which might be lurking at the farthest reaches of our cosmic neighborhood. This is not Pluto, which was demoted from planet status to dwarf planet in 2006. From its discovery in 1930 until 2006, Pluto was considered the 9th planet in the solar system. The first astronomer to propose the existence of a trans-Neptunian population was Frederick Leonard. On August 24, 2006, the International Astronomical Union, IAU, defined the term planet for the first time. Pluto did not fit this definition, and the IAU classified it as a dwarf planet. Scientists believe that Planet 9 is a gas or ice giant located billions of miles from the other planets. It's very hard to explain the solar system without Planet 9, but it's impossible to be 100% sure of its existence until you see it, said Mike Brown. The idea of a 9th planet first emerged after the discovery of Uranus in 1781 by English astronomer William Herschel and Neptune on September 24, 1846 by J. Gall and his assistant d'Arrest, which proved that the solar system is much larger than previously thought, and that other worlds may still be waiting to be discovered. If it exists, its discovery would be the most significant finding in the solar system in a century, and would help better understand the origin and evolution of giant planets both in our system and in other star systems. Over the past 20 years, a complex orbital structure has been discovered on the outskirts of the solar system. These belong to cold objects from the Kuiper Belt, a region of the solar system extending from Neptune's orbit to about 55 AU from the Sun, that orbit beyond Neptune. The Kuiper Belt primarily consists of small bodies, the material left over after the formation of the solar system. The objects are mainly composed of volatile substances, known as ices, such as methane, ammonia, and water. At least 4 dwarf planets are located in this region of near space. Pluto, discovered on February 18, 1930, the largest known dwarf planet in the solar system. Haumea, discovered on July 29, 2005. Makemake, discovered on March 31, 2005. And Eris, discovered on January 5, 2005, the second largest after Pluto, the most massive, and the farthest dwarf planet from the Sun in the solar system. Moreover, it is believed that some of the moons of the solar system's planets, such as Triton, Neptune's largest moon, discovered by English astronomer William Lassell on October 10, 1846, and Saturn's moon Phoebe, the most massive of Saturn's distant irregular moons, discovered by W. Pickering in 1899, also originated in this region. Celestial mechanics are well studied enough to confidently assert that the appearance of these orbits cannot be explained solely by the influence of the 8 known planets. The gravitational forces and interactions created by the known objects in the solar system are incapable of forming such a complex and stable architecture of orbits. This fact points to the presence of an unknown source of gravitational influence that could explain the observed anomalies. Such a source might be a hypothetical new planet located on the outskirts of the solar system, whose gravitational influence forms these unusual orbits. If confirmed, its existence would significantly expand our understanding of the structure and dynamics of the solar system. Technically, the mystery of the ninth planet began in 1992, when the first trans-Neptunian bodies were discovered, objects orbiting our star at a distance greater than Neptune's orbit. This discovery sparked a debate regarding Pluto and led scientists to conclude that it was merely the first discovered object in the Kuiper belt. A few years later, after thoroughly studying the orbits of these objects, a strange pattern became evident. The motion of such bodies could no longer be explained by the gravitational influence of Neptune or other planets in the solar system. All the calculations led to the conclusion that the hypothesis of a ninth planet in the solar system should be reconsidered. The first proposal from astrophysicists regarding a new planet came in 2002. The sharp decrease in the number of Kuiper belt objects was attributed to the influence of a planet the size of Mars located at 60 astronomical units. However, it turned out that the calculations did not match the observations. Similar unsuccessful hypotheses emerged in 2008 to explain more subtle properties of the Kuiper belt. Other ideas were proposed after the discovery of more distant objects loosely associated with Neptune, such as 2000 CR 105. Its orbit could have been explained by an interaction with a new planet, but it turned out that it could be fully explained by the influence of known planets. On the other hand, the orbit of Sedna, whose perihelion, the closest point to the Sun, is 76 astronomical units, can indeed only be explained by an external influence, either by a planet or by nearby stars. However, in a 2006 study, numerical modeling showed that the orbits of 2000 CR 105 and Sedna could be explained by a planet with a mass between Neptune and Jupiter, located at a distance of 100 to 1000 astronomical units. An independent hypothesis was put forward in 2014 after the discovery of a new small body, 2012 VP 113, far beyond the sphere of influence of the planets. Astronomers noticed that the perihelion of objects beyond 150 astronomical units is clustered in a small area of space. Astronomers suggested that a planet with a mass several times that of Earth could maintain such a grouping through the Kozai-Lidov resonance. A body with a mass of 5 Earth masses in an orbit with a radius of 210 astronomical units could stabilize the orbit of 2012 VP 113. But it was not possible to explain the stabilization of other similar objects' orbits using the same mechanism. Ultimately, it turned out that the explanation using the Kozai-Lidov resonance requires the simultaneous existence of several planets. In 2017, it was discovered that the plane of the belt within 50 to 80 astronomical units is unusually tilted relative to the solar system. A Mars-sized object on a highly inclined orbit was proposed. Such an orbit is theoretically possible, but the object would be brighter than 17th magnitude. So over 170 years, several planets beyond Neptune have been proposed, but all these hypotheses rely on selective data analysis. The evidence supporting the hypothesis of the existence of a ninth planet is primarily related to the unusual orbits of several trans-Neptunian objects, TNOs, which cannot be explained solely by the gravitational influence of the known planets in the solar system. One such object is Sedna, which was discovered on November 14, 2003, by American astronomers Brown, Trujillo, and Rabinowitz. Sedna attracted the attention of astronomers with its unusual orbit, characterized by an extremely large aphelion and perihelion. Sedna's perihelion is 2.5 times farther from the Sun than Neptune's orbit, and most of its orbit lies even farther away. The aphelion is approximately 960 AU, which is 32 times the distance from the Sun to Neptune. Sedna's orbit has a period of about 11,400 years, making it one of the most elongated among known objects in the solar system. Such an orbit cannot be explained by the gravitational influence of Neptune or other known planets. These features have led scientists to consider the existence of a massive object in the solar system that could be influencing the orbits of objects like Sedna. Other examples of unusual TNOs include objects such as 2012 VP 113, 2004 VN 112, 2007 TG 422, 2015 TG 387, and 2004 XR 190. 2012 VP 113, also known as Biden, was initially discovered on November 5, 2012, in one of the images taken with the dark energy camera mounted on the 4-meter Victor Blanco telescope at the Cerro Tololo Inter-American Observatory. Subsequent observations confirmed that this is a large, previously unstudied object, whose orbit reaches a maximum distance of 452 AU from the Sun. To study the orbit and surface of 2012 VP 113, the 6.5-meter Magellan telescope of the Carnegie Institution in the Las Campanas Observatory, Chile, was used. 2004 VN 112 was discovered on November 6, 2004, during observations at the Cerro Tololo Observatory, and it is, on average, located more than 300 AU from the Sun. Upon discovery, the object was designated 2004 VN 112, later assigned number 474640, 2004 VN 112, and then it was named after the Alicanto bird. This is a giant bird from Chilean miners' mythology, with metallic-colored wings, a powerful hooked beak, and predatory claws. The orbit of 2004 VN 112 is characterized by high eccentricity, 0.850, a moderate inclination, 25.58 degrees, and a semi-major axis of about 316 AU. As of January 11, 2017, the orbit was calculated based on 34 observations over a 5,821-day observation arc and has an absolute magnitude of 6.5. The object was subsequently found in sky images starting from September 26, 2000. Michael Brown's website lists this object as a minor planet with a diameter of approximately 314 kilometers. The visible spectrum of 474640, Alicanto, differs from Sedna's spectrum. The slope of the spectrum suggests that the object's surface may contain pure methane ice and amorphous silicates. 2007 TG 422 is a scattered disk object discovered on October 3, 2007 at the Apache Point Observatory. 2007 TG 422 passed perihelion in 2005 at a distance of 35.5 AU from the Sun. Until 2018, the object was visible in the constellation Taurus, and its opposition was observed on November 29, 2017. The orbital parameters of 2007 TG 422 vary depending on the epoch. In 2007, its orbital period was estimated at 10,611 years, with an aphelion distance of 930 AU, but by 2012, these parameters had changed. The period increased to 13,512 years, and the aphelion distance to 1,099 AU. Due to the high eccentricity of its orbit, barycentric coordinates for such objects are more stable than heliocentric ones. According to the JPL Horizons Ephemeris system, as of May 14, 2018, the barycentric orbital parameters of 2007 TG 422 are as follows. The semi-major axis is 503 AU, and the orbital period is about 11,300 years. For comparison, Sedna has a larger semi-major axis and orbital period. 2007 TG 422 has been observed 98 times over 7 years and has an uncertainty parameter U equals sign 2. The object has not been observed since 2015. 2015 TG 387, Leleaku Honua, is a trans-Neptunian object in the outer solar system, a sednoid. It was previously known by the nickname Goblin. It is the third known object after Sedna and 2012 VP 113. It was first observed on October 13, 2015 by astronomers David Tholen, Scott Shepard, and Chad Trujillo using the Subaru telescope at the Mauna Kea Observatory. The object's diameter is 300 kilometers. At the time of the announcement of its discovery on October 1, 2018, the observation arc was 949 days. In perihelion, 2015, TG 387 approaches the Sun, at a distance of about 65 astronomical units. Only Sedna and 2012 VP113 have more distant perihelia, with the closest perihelion passage expected in 2078. In aphelion, it is about 2,000 astronomical units from the Sun, while other data suggests it is 2,300 AU away. The orbital period around the Sun is 39,100 years. The orbit of 2015 TG 387 is consistent with the hypothesis of a ninth planet. 2004 XR 190 is a detached trans-Neptunian object, a candidate for a dwarf planet, located in the scattered disk. Astronomers led by Lynn Jones from the University of British Columbia discovered it as part of the Canadian-French CFEPS program using a telescope in Hawaii, CFHT. The discovery team temporarily nicknamed the object Buffy, after Buffy the Vampire Slayer from TV shows. According to the discoverer Lynn Ellen Jones, the object could kill the existing theory of the origin of the solar system, just as Buffy kills vampires. The detached trans-Neptunian object 2004 XR 190 is quite unusual for two reasons. Its orbital inclination is 47 degrees. Such an inclined orbit means the object moves around the Sun, traveling up and down rather than left to right when viewed edge-on along the ecliptic. Secondly, the object has an unusually close to circular orbit for a scattered disk object. While the hypothesis has been proposed that scattered disk objects were ejected into their current orbits due to Neptune's gravitational influence, with significant perihelion distances, it is difficult to reconcile all these orbital configurations with the laws of celestial mechanics. This has led to some uncertainty in existing theoretical models of the outer solar system. How might new discoveries in the outer solar system confirm or alter the hypothesis of a ninth planet? Recent research conducted by Konstantin Batygin, 1986, an American astrophysicist, and Michael Brown, 1965, a professor of planetary astronomy at the California Institute of Technology, has significantly contributed to the development of the hypothesis regarding the existence of a ninth planet. As part of these studies, the scientists conducted a series of computer simulations aimed at determining the possible parameters of the hypothetical planet, based on the observed characteristics of the orbits of trans-Neptunian objects, TNOs. The results of the simulations provided more precise characteristics of the ninth planet, which had previously been uncertain. One of the key conclusions drawn from these studies was the hypothesis regarding the mass of the ninth planet. According to the models by Batygin and Brown, the hypothetical planet could have a mass 10 times greater than that of Earth. This makes it a significant object, comparable in mass to icy giants such as Uranus and Neptune. This mass also explains its ability to exert substantial gravitational influence on TNOs, affecting their orbits and causing the observed anomalies. Furthermore, the simulations allowed the scientists to refine the orbital parameters of the ninth planet. It is estimated that its orbit would be highly elongated with an eccentricity, elongation, that greatly exceeds the eccentricity of the orbits of the other planets in the solar system. The orbit of the ninth planet, according to the models, lies at a distance of 400 to 800 astronomical units, AU, from the Sun. Due to these orbital parameters, the planet could be moving along an orbit that is highly inclined relative to the plane of the ecliptic, the plane in which the other planets of the solar system orbit, which also explains its long presence in distant regions where its light is too faint to be detected from Earth. The models also suggest that a complete orbit of the ninth planet around the Sun could take 15,000 years, which explains why it has not been observed for millennia. Recent studies have also suggested that the orbit of the ninth planet may be the cause of the grouping of the orbits of certain TNOs. Objects such as Sedna, 2012 VP113, and others exhibit unusual orbital characteristics that cannot be explained solely by the influence of the known planets. The computer models by Batygin and Brown indicate that the presence of a massive planet on the periphery of the solar system could explain these anomalies, including the group of TNOs with elongated orbits and their orientation in space. The hypothesis of the existence of a ninth planet, proposed by Konstantin Batygin and Mike Brown, has led to intense debates and a surge in scientific research. The scientific community's reaction to this hypothesis has been diverse. though predominantly positive, albeit with a certain degree of skepticism. On one hand, many astronomers have been inspired by the new opportunities to explore distant regions of the solar system, leading to a series of new observational programs and theoretical studies. On the other hand, the existence of the ninth planet remains unconfirmed, which raises doubts and requires more convincing evidence. Immediately following the publication of the hypothesis in 2016, the scientific community split into several camps. Some scientists saw the proposal as a logical explanation for the observed anomalies in the motion of trans-Neptunian objects, TNOs. These anomalies, including the clustering of TNO orbits, could not be explained solely by the influence of known planets. The ninth planet hypothesis offered a potential solution to this mystery and a new perspective on the dynamics of the outer solar system. Other scientists approached the hypothesis with caution. They pointed out that the observed orbital anomalies might result from other processes, such as interactions with the galactic tide, mass distribution in the Kuiper belt, or even errors in observational data. In response to these arguments, additional studies were conducted to refine and verify the data, ultimately leading to a deeper understanding of TNO dynamics and the potential existence of large planetary bodies at the solar system's periphery. The statistical confidence in the existence of the ninth planet, achieved by scientists based on the latest models, stands as one of the most compelling arguments in favor of this hypothesis. The 5 sigma level of statistical significance, derived from the analysis of the orbital data of trans-Neptunian objects, TNOs, virtually rules out the possibility that the observed anomalies in their movement could be random. For comparison, this level of significance is used in physics to confirm the discovery of new elementary particles, such as the Higgs boson. 5 sigma means that the probability of error or coincidence is 1 in 3.5 million, making the ninth planet hypothesis statistically highly credible. This result was obtained through a meticulous analysis of the orbits of 13 trans-Neptunian objects, whose parameters show a clear clustering in space that cannot be explained by the influence of known planets. The models developed by Batygin and Brown account for all possible factors that could affect these orbits, and conclude that the only plausible explanation is the presence of a massive celestial body on the periphery of the solar system. However, despite such high statistical confidence, the question of the ninth planet's existence remains open. Could it be that our understanding of gravitational interactions within the solar system is still incomplete, and that there are other factors capable of explaining the observed anomalies? Or is there indeed another planet lurking at the edge of the solar system, whose existence challenges current conceptions of the structure of our planetary system? It is worth noting that the 5 sigma level of statistical significance was first used in astrophysics in 2012 to confirm the existence of a new elementary particle, the Higgs boson. This discovery was a revolutionary event in physics and led to the revision of many theoretical models. The application of such a stringent criterion in the case of the ninth planet shows how seriously scientists take this hypothesis and how convincing the modeling results appear. Nevertheless, in astronomy, as in other sciences, not only statistical analysis, but also direct observation is crucial. Without actual observation of the ninth planet, its existence remains a hypothesis, albeit a highly probable one. If the ninth planet indeed exists, what other surprises might it hold? What will its physical characteristics be? And could there be something even more mysterious hidden beyond its orbit? With each new step in the search for this planet, scientists come closer to answers. But is there something still eluding our attention? Models based on the hypothesis of the existence of a ninth planet indicate its significant influence on the dynamics of objects in the distant regions of the solar system. One of the most intriguing features of these models is the ninth planet's ability to explain the clustering of orbits of certain trans-Neptunian objects, TNOs. The clustering observed in the orbits of such objects as Sedna, 2012 VP 113, and others, lies in the fact that their perihelia, points of closest approach to the Sun, are grouped in one direction, which should not occur randomly. Under the influence of only the known planets, such as Neptune, these objects should have gradually scattered along their orbits, losing such a clear orientation in space. However, the presence of a ninth planet with its massive gravitational field could maintain the TNOs in these orbital configurations. It is also hypothesized that the influence of the ninth planet extends far beyond the Kuiper belt, affecting objects located hundreds of astronomical units away from the Sun. The gravitational pull of this planet could stabilize the orbits of such objects, preventing their disruption or ejection from the solar system due to interactions with Neptune or other gas giants. An important aspect of this influence is the ninth planet's ability to counteract gravitational perturbations from Neptune. In the absence of the ninth planet, TNOs with elongated orbits would experience strong perturbations, especially if their orbits intersect with Neptune's. However, models suggest that the ninth planet could act as a stabilizer, preventing such perturbations and ensuring the long-term stability of the TNO's orbits. This explains why objects like Sedna and 2012 VP-113 remain on their unusual orbits despite potential gravitational influences from other planets. The large-scale influence of the ninth planet could also explain the presence and behavior of other small bodies in the distant regions of the solar system. For instance, it might be responsible for the formation of groups of objects with specific orbital inclinations, or for the existence of objects with extremely elongated orbits, which cannot be explained within the framework of current models without considering its gravitational impact. If its influence is indeed so substantial, could there be something even more significant behind it? What other undiscovered forces might be at work on the fringes of our planetary system? There are alternative theories that attempt to explain the observed anomalies in the orbits of trans-Neptunian objects, TNOs, without the need for a hypothetical ninth planet. Although these theories are less popular, they offer intriguing and potentially explainable scenarios that take into account other factors, such as the Oort cloud, galactic tides, or even the possibility of a primordial black micro-hole. One such alternative is the hypothesis that the anomalous TNO orbits might be the result of the influence of the Oort cloud, a vast region containing billions of cometary bodies located between 50,000 and 100,000 AU from the Sun, roughly a light-year away. The Oort cloud is thought to include two distinct regions, a spherical outer cloud and an inner disc-shaped region. The objects in the Oort cloud are largely composed of water, ammonia, and methane ices. Astronomers believe that these objects formed near the Sun and were scattered far into space by the gravitational effects of the giant planets during the early stages of the solar system's development. The Oort cloud remains poorly studied, and its existence has only been confirmed through indirect evidence. However, scientists speculate that it might exert a gravitational influence on TNOs, causing the clustering of their orbits and other anomalous phenomena. Another theory suggests that galactic tides, that is, forces acting on the solar system from the Milky Way, could influence the orbits of TNOs. Galactic tides arise from the uneven distribution of mass in the galaxy and can cause slow changes in the orbits of objects at the edge of the solar system. In this context, scientists consider the possibility that these galactic tides, rather than a ninth planet, are responsible for the observed clustering of orbits. These tides could explain the anomalies without requiring the existence of an unknown large object in the solar system. An even more exotic hypothesis proposes that instead of a planet, a primordial black microhole might exist at the outskirts of the solar system. Primordial black holes are hypothetical objects that could have formed right after the Big Bang, and unlike ordinary black holes, may have a mass significantly smaller than that of stellar black holes. If such a microhole has a mass comparable to that of the ninth planet, about 5–10 Earth masses, it could exert a similar gravitational influence on TNOs, creating the same anomalies in their orbits. Scientists at Durham University in the UK suspect that instead of the ninth planet that researchers have been trying to detect recently, a small black hole might actually be roaming the edges of the solar system. This theory was discussed in the journal New Scientist. However, detecting such a black hole would be extremely challenging, as it does not emit light and can only be detected by its gravitational effects. Despite the appeal of these alternative theories, each of them faces certain challenges and requires additional data for confirmation. Each theory adds intrigue to current research, and in the coming years, scientists may find an answer that will revolutionize our understanding of the structure of the solar system. The hypothesis that the proposed ninth planet is actually a primordial black hole opens up a completely new perspective on possible objects lurking in the distant corners of the solar system. Unlike ordinary black holes, which form from the collapse of massive stars, primordial black holes can be very small in size and have masses comparable to those of planets. One of the main arguments supporting this hypothesis is the fact that black holes of this size do not emit any light and can only be detected through their gravitational effects. However, if the ninth planet is indeed a primordial black hole, astronomers face a new challenge: how to detect an object that is virtually invisible to our telescopes. European physicists have developed an approach that uses data on the oscillations of the orbits of global navigation system satellites to search for possible traces of the existence of so-called primordial black holes. These measurements can help to find or significantly narrow down the field of permissible sizes and masses of these objects, the researchers write in a paper published in the electronic library arxiv.org. We have proposed for the first time to use measurements from gravimetric scientific instruments and the orbital parameters of global navigation system satellites to search for anomalies caused by clusters of dark matter and primordial black holes that approach Earth at a sufficiently close distance. The effectiveness of this approach has already been tested using one of the satellites of the Galileo navigation system. The strength of this radiation is too weak for such black holes to be detected by any existing telescopes. A group of European physicists, led by Professor Sebastian Claes from the Free University of Brussels, Belgium, has developed an approach that indirectly uses existing navigation satellites to search for primordial black holes in the near vicinity of Earth, as well as to search for small clusters of dark matter. Guided by these considerations, the scientists calculated how well a single satellite from the Galileo navigation system, or the entire fleet of these probes, would be able to detect primordial black holes. These calculations showed that a single satellite could detect such objects at a relatively short distance from Earth, about 1.5 astronomical units, the average distance between the Sun and our planet. But combining data from a large number of satellites would dramatically expand the search limits for primordial black holes. Nevertheless, the hypothesis of a primordial black hole remains highly speculative and requires further research and observation. So, is the ninth planet a lost planetary body, or is it one of the first black holes in the universe, hiding right under our noses? One of the most significant challenges astronomers face in the search for the ninth planet is its presumed immense distance from the Sun. At such a distance, sunlight becomes so weak that the planet receives thousands of times less light than Earth. This means that its albedo, the ability to reflect sunlight, is extremely low, making it virtually invisible to most telescopes. The vast distance and faint brightness make the ninth planet extremely difficult to observe, even with the most powerful ground-based and space telescopes. For example, telescopes like Subaru, an 8.2-meter optical telescope owned by the National Astronomical Observatory of Japan and located at the Mauna Kea Observatory, and the James Webb Space Telescope, with its large 6.5-meter diameter mirror located at the Lagrange point L2, while highly sensitive, may still struggle to detect an object with such low levels of illumination. Even if the planet does exist, its visible brightness, or apparent magnitude, might be so small that it gets lost among the millions of other stars and objects in deep space. Another difficulty is that, according to models, the ninth planet not only has a large distance from the Sun, but also follows a highly elliptical orbit. Such an orbit could take from several thousand to tens of thousands of years to complete a full revolution around the Sun, and depending on the current position of the planet, its detection could be even more challenging. If the planet is at the aphelion of its orbit, its farthest distance from the Sun, it would be even dimmer and harder to observe. Additionally, the planet's slow movement in its orbit means that reliable detection requires years of observation. If astronomers detect an object that matches the parameters of the ninth planet, they will need to confirm its orbital motion, which can take years. Such long-term observations require significant resources and careful planning, as telescopes capable of such studies are often occupied with many other scientific projects. Modern astronomical observation methods also face several technical limitations. For instance, ground-based telescopes are affected by atmospheric and weather conditions that can distort images. Space telescopes, like the James Webb Space Telescope, although free from these issues, face limitations regarding observation time and spatial orientation. The search for the ninth planet remains one of the most exciting challenges in modern astronomy. Leading observatories around the world continue intensive observations of the distant edges of the solar system, using both ground-based and space telescopes. Each of these tools has unique capabilities that may play a key role in detecting the hypothetical object whose gravitational effects are felt on the orbits of trans-Neptunian objects, TNOs. One of the most promising tools for finding the ninth planet is the Vera C. Rubin Observatory, set to begin operations in January 2025. The official start date for the project is considered August 1st, 2014, with construction on site beginning April 14th, 2015. The telescope will be located at the peak of El Peñón on Cerro Pachón mountain in the Coquimbo region of northern Chile, near the existing Gemini and Southern Astrophysical Research telescopes. The LSST, Legacy Survey of Space and Time Architecture, is unique among large telescopes with an 8-meter mirror and is designed based on the Paul Baker 3-element scheme. This design is capable of providing a very wide field of view. Its diameter is 3.5 degrees and its area is 9.6 square degrees. Achieving such a very wide, undistorted field of view requires 3 mirrors instead of the 2 used by most existing large telescopes. The primary mirror has a diameter of 8.4 meters. The secondary mirror is 3.4 meters, and the diameter of the tertiary mirror, located behind a large opening in the primary mirror, is 5 meters. A digital camera with a 3.2 gigapixel matrix, composed of 189 light-sensitive CCD matrices operating in the ultraviolet, visible, and infrared ranges, will take 15-second exposures every 20 seconds. Given maintenance, poor weather, etc., the camera is expected to take about 200,000 photographs, 1.28 petabytes in uncompressed form, per year, which is far more than can be examined by humans. This telescope in Chile will conduct large-scale sky surveys known as the Legacy Survey of Space and Time, LSST. The LSST survey will cover significant portions of the sky with high sensitivity and frequency of observations, enabling the detection of slowly moving objects on distant orbits, such as the ninth planet. One of the strengths of the LSST is its ability to detect faint objects that might be missed by other telescopes. The Nancy Grace Roman Space Telescope, officially assigned to NASA's mission on February 17, 2016, and scheduled for launch in 2027, is also expected to contribute to the search. The telescope will be used to address tasks such as counting the number of exoplanets in a given galaxy and observing the distribution of galaxies to study dark matter. One of the advantages of Roman will be its large field of view and its ability to take images very quickly. According to digital trends, it will be 1,000 times faster than the Hubble. The Goddard Center estimates that Roman will take about 100,000 images per year. Additionally, ground-based telescopes, such as the ALMA, Atacama Large Millimeter Submillimeter Array, in Chile with its 66 high-precision antennas, and other radio telescopes, can assist in the search through observations of faint radio emissions from TNOs and other objects in this remote region of the solar system. These telescopes can detect weak but significant signals that may indicate the presence of the ninth planet. In 2022, researchers using the ALMA telescope reported that they had detected 2 distant cosmic objects, and other astronomers have suggested that this might be evidence of Planet X, the ninth planet of the solar system, in a serious astronomical journal. It is also possible that missions aimed at exploring the outer regions of the solar system, such as Voyager 1 and 2, launched in 1977, New Horizons, launched on January 19, 2006, and future missions to Jupiter and Saturn could accidentally detect signs of the ninth planet. Such missions often uncover unexpected phenomena making them potential contributors to solving this mystery. If Planet 9 is discovered in the future, how long would a journey to it take? Some experts believe that we are only a few years away from either discovering or definitively ruling out the existence of this hypothetical world. If Planet 9 is ever found, space agencies like NASA would want to send a probe to visit this distant world. However, they would first need to plan and gain approval for such a mission. It will take at least a decade or more, Andreas Hein, a space systems engineer at the University of Luxembourg, told Live Science in an email. This is mainly due to the fact that missions must undergo a lengthy and rigorous government selection process, he added. However, this process could be expedited depending on how unusual the world appears in initial observations, said Manasvi Lingam, a theoretical astrobiologist at the Florida Institute of Technology, in an email to Live Science. If Planet 9 is anomalous in some respect, there might be greater interest in accelerating such a mission. According to Hein, a private space company like SpaceX could potentially launch missions sooner, possibly within 5 years of the discovery, since they are less hindered by such bureaucracy. Once a probe is sent to Planet 9, the next question is, how long will it take to get there? In 2022, Hein, Lingam, and astronomer Adam Hibbard attempted to answer this question in a theoretical paper published on the preprint server RSIV. In this non-peer-reviewed paper, the researchers estimated that a spacecraft similar to NASA's Voyager probes would likely take between 45 and 75 years to reach Planet 9. These estimates were based on the assumption that Planet 9 is, on average, about 400 astronomical units from the Sun, or 400 times farther from the Sun than Earth. While 75 years may seem like a long time for a one-way trip, it is relatively quick compared to the journeys of existing probes. Mike Brown initially estimated that a probe could potentially reach Planet 9 in just 20 years. However, Lingam noted that it is difficult to understand how it could reach the planet so quickly with current technology. According to Hein and Lingam, reaching Planet 9 could be faster if we were able to master more advanced propulsion technologies, such as light sails, giant sails that capture sunlight, or lasers to accelerate spacecraft. In their 2022 study, scientists estimated that a light sail might take just 7 years to reach Planet 9. However, the team estimates that light sails may not become a reality for at least 20 years. As a result, if we were to find Planet 9 tomorrow, it would be better to send a contemporary probe rather than wait for alternative technologies to develop, said Lingam. Laser sails could be launched later, if and when they become practical and cost-effective. As propulsion systems continue to advance, sending humans to Planet 9 may also become possible, but likely not in the near future. This discovery could be a significant step in understanding the dynamics of planetary system formation, which has direct implications for the search for extraterrestrial life. The influence of massive objects, such as the hypothesized ninth planet, could lead to substantial changes in the architecture of a planetary system. They could act as sources of gravitational perturbations, which in turn might affect the orbits of exoplanets, especially those located within their star's habitable zone. These perturbations could facilitate the migration of planets to orbits where liquid water, a key component for the emergence of life as we know it, could exist. Additionally, gravitational interactions with large objects could influence the stability of climatic conditions on exoplanets, which is also a crucial factor for sustaining life. In turn, understanding these processes could enhance our ability to assess conditions on distant exoplanets, thereby increasing the chances of discovering habitable worlds. Further study of the hypothesized planet could provide new insights into the mechanisms that determine conditions conducive to the emergence of life. This knowledge could become a key element in the search for other worlds capable of supporting life and may potentially lead to significant discoveries in astrobiology and cosmology. The study of the possible orbit of a new planet in the solar system inevitably leads to comparisons with exoplanets in other stellar systems. The orbital characteristics of the hypothetical ninth planet allow parallels to be drawn with planets discovered in other parts of the galaxy. One interesting object for such comparison is the exoplanet discovered in the TRAPPIST-1 system. located in the constellation Aquarius, 39.5 light-years from the Sun. This system is known for having several planets within its star's habitable zone. Of particular interest is the exoplanet TRAPPIST-1d, which orbits the star TRAPPIST-1 in Aquarius. Its orbit and characteristics might provide useful data for understanding the dynamics of planets in similar conditions. Comparing the orbital parameters of the new planet in the solar system with such exoplanets could help assess its potential stability and interactions with other celestial bodies. Comparing the ninth planet with exoplanets discovered in other systems offers a deeper understanding of how universal the processes of planet formation and evolution might be. This opens new horizons in planetary system research and allows the use of data from other systems to refine hypotheses related to the ninth planet. One key question arising from the comparison of the ninth planet's orbit with those of exoplanets is the influence of neighboring stars on the formation and evolution of orbits. In the case of the solar system, such influence could explain the elongated orbit of the ninth planet, if it indeed exists. This also raises questions about the importance of considering external factors when modeling planetary systems, especially at large distances from the central star. An important aspect of comparing the ninth planet with exoplanets is understanding the processes of planetary migration within planetary systems. If the ninth planet did indeed migrate to its current orbit during the formation of the solar system, it could provide new data on how large planets can move within their systems, altering their structure and dynamics. Studies of exoplanets with similar orbits could confirm or refute such migration scenarios, significantly expanding our understanding of these processes. Could this information also lead to new discoveries within our own solar system? Scientists have hypothesized that observations leading to the suggestion of a ninth planet in the solar system might indicate the presence of a modified law of gravity. This new theory posits that our current understanding of gravity might be insufficient to explain all observed astronomical phenomena. If validated, it could radically alter our understanding of gravitational interactions and the structure of the solar system. American physicists presented a new study in the Astronomical Journal claiming that data from the outer reaches of the solar system, suggesting the existence of a ninth planet, might also point to another significant factor. Researchers believe that a modified law of gravity could exist in the solar system, originally proposed as a hypothesis to explain galaxy rotation, according to Phys. An alternative theory to Isaac Newton's law of gravitation is modified Newtonian dynamics, MOND. This hypothesis suggests that galaxy rotation can be explained without dark matter, which current theories use to account for gravitational effects. MOND asserts that Newton's law of gravitation is applicable up to a certain level of gravitational acceleration, beyond which gravity behaves differently. MOND can account for processes within galaxies, but recent research indicates it might also impact the outer regions of the solar system. Scientists concluded that if gravity were governed by MOND, the Milky Way could significantly influence objects at the outer boundaries of our system. This hypothesis emerged from observations that uncovered anomalies in the orbits of objects at the edge of the solar system. Such anomalies previously led to the discovery of Neptune. Initially, MOND was thought to contradict the data that prompted the search for a ninth planet. However, research has shown that MOND predicts the existence of anomalous orbits observed by astronomers. The new hypothesis suggests that, over time, the orbits of certain objects at the edge of the solar system could align with the gravitational field of the Milky Way. While this hypothesis seems promising, the lack of extensive data prevents a more definitive conclusion about the presence of an alternative law of gravity in the solar system. The discovery of a ninth planet in the solar system could radically alter our understanding not only of our own planetary system, but also of the principles governing the formation and evolution of planetary systems in other parts of the galaxy. Currently, scientists are actively studying numerous exoplanetary systems, with each new discovery contributing to the broader picture. However, the ninth planet might shed light on unique processes that could be common to many planetary systems, or conversely, specific only to the solar system. One of the main reasons why the discovery of a ninth planet could change our view of cosmic architecture is its presumed characteristics. If the ninth planet indeed exists, and has a mass several times greater than that of Earth, It would imply that our solar system is capable of forming and maintaining objects of significant mass on extremely distant orbits. This finding would challenge existing theories about how planets form and migrate during the early periods of stellar system evolution. According to current models of planetary system formation, gas giants and ice planets form at certain distances from their star and can subsequently migrate closer to or farther from the star, depending on various dynamic processes. However, the presence of a massive planet on such a distant orbit in the solar system might necessitate a revision of these models, as it would suggest that our system is capable of maintaining such objects on stable orbits even at distances of hundreds of astronomical units from the Sun. Moreover, such a discovery could stimulate a re-evaluation of observations of other stellar systems, where similar planets might exist but have remained unnoticed due to their distance from their stars. This could lead to the development of new methods and strategies for searching for such planets in other systems, thereby expanding our understanding of possible scenarios for planetary system formation. The discovery of a ninth planet also has the potential to impact theories regarding the existence of so-called super-Earths, planets with masses significantly greater than Earth's, but located on orbits much farther out than traditionally expected. If the solar system can have such a planet, then similar objects might also exist in other systems, which would significantly alter our understanding of how frequently different types of planets are found in the galaxy. Future discoveries in astronomy could have a decisive impact on the hypothesis of a ninth planet, and the coming years will be a critical period for resolving this issue definitively. Observations conducted using both ground-based and space telescopes could provide the necessary evidence to either confirm or refute the existence of this mysterious planet. In addition to projects like the Vera C. Rubin Observatory and planned space missions such as the Nancy Grace Roman Telescope and the James Webb Space Telescope, NASA is planning to launch a next-generation telescope in the 2030s called the Habitable Worlds Observatory, HWO. This telescope will feature a high-tech sunshield that will reduce the glare from stars with Earth-like planets, allowing HWO to finally detect and study the atmospheres of these planets in search of life and potentially discover new planets. By the end of this decade, the Extremely Large Telescope, ELT, is also expected to come online. Although it will not venture into space, it will observe the sky from the depths of the Chilean desert, where the air is crystal clear. This telescope will have a record-breaking 39-meter mirror, enabling it to study the atmospheres of distant planets with unprecedented resolution. All of these telescopes use spectral analysis technology, which has long been used to determine the chemical composition of substances. The difference is that these powerful telescopes can make inferences from a single beam of light emitted by the atmosphere of one of the planets being studied, located hundreds of light-years away. Equally important is the upcoming European Space Agency's Euclid project. This space telescope was developed and built with the participation of many ESA member states. The observatory consists of a 1.2-meter Korsch telescope, a VIS camera, and a NISP spectrometer and photometer, which conduct observations in the optical and near-infrared ranges. Although the primary goal of this mission is to study dark energy and dark matter, its capabilities may be utilized in the search for the ninth planet. With its unique capabilities, Euclid might accidentally discover the ninth planet. Even if the ninth planet hypothesis is not confirmed, it will not mark the end of research. Astronomers will develop new theories to explain the strange orbits of trans-Neptunian objects, possibly considering other factors. The coming years could be pivotal in solving the mystery of the ninth planet. Observations using advanced technologies will help not only answer the question of its existence, but also expand our understanding of the processes shaping the structure and evolution of planetary systems. Regardless of whether the hypothesis is confirmed, research aimed at finding it will inevitably lead to new discoveries and help answer fundamental questions. Research in astronomy continues to amaze with discoveries related to celestial bodies in the distant parts of our solar system. One of the most discussed topics is the existence of the so-called Planet 9 Inches and its connection to the TNOs 14 meteorite. Scientists are investigating an area known as the Eternal Night, which lies beyond the planetary orbits and represents the trans-Neptunian space. In this remote region, astronomers have discovered a population of celestial objects known as trans-Neptunian objects. Some researchers believe that this population might be linked to the existence of a new, yet undiscovered planet in the cold and distant parts of the solar system. However, opinions among scientists are divided. Some believe that these observations could indicate the presence of Planet 9, while others are skeptical, pointing to the possibility of inaccuracies in the observations. Detecting such distant objects requires powerful telescopes, but most modern instruments have limited fields of view. In this context, scientists have been drawn to the TNOs 14 meteorite, also known as the first interstellar meteor, IM-1, which fell on January 8, 2014, in the Bismarck Sea of the Pacific Ocean, a few kilometers north of Manus Island. Researchers from Harvard suggest that this meteorite might not have originated from our solar system, which could point to a connection with Planet 9. Scientists constructed a model of the potential orbit of Planet 9 and overlaid it on the meteorite's trajectory. They found a match between the meteorite's landing site and the region where Planet 9 might be located. The probability of a random coincidence of these data is only 1%. Furthermore, scientists reconstructed the trajectory of TNOs 14 and identified 3 anomalies. This leads to the hypothesis that there is a 99.9% chance that the meteorite collided with an unknown planet in the outer part of the solar system. According to this hypothesis, the meteorite might have been directed onto our orbit by a large object, such as Planet 9, approximately 30 and 60 years ago. If this assumption is correct, by tracing the trajectory of TNOs 14 back in time, scientists could determine the location of Planet 9 near the intersection of the constellations Aries, Taurus, and Centaurus. How might artificial intelligence impact the search for the 9th planet in our solar system, and what specific examples of its application could alter our approaches to this task? Artificial intelligence, AI, and machine learning, ML, are becoming indispensable tools in astronomy, particularly in the search for the 9th planet. Modern telescopes and astronomical observatories generate vast amounts of data that need to be analyzed to detect subtle deviations or objects indicating the presence of a hypothetical 9th planet beyond Neptune's orbit. Traditional methods for processing such data require significant time and human resources. AI and ML enable automation and significantly accelerate this process. In space research, collecting and processing enormous amounts of data is essential. Consequently, ML algorithms have been employed in the space industry since the 1990s. For example, the Palomar Observatory has used the SkyCat AI system for classifying objects from low-resolution images since 1994. The Hubble telescope has been equipped with AI algorithms since 1993. Today, machine learning is used in various fields, from astronaut training and rocket science to discovering new laws in astrophysics. China, the United States, Russia, and Japan have recognized the development of AI as a strategic component in their space programs for the coming years. According to forecasts from International Data Corporation, IDC, spending on ML systems was expected to reach $97.9 billion in 2023. Researchers from Northwestern University in Chicago and Tsinghua University in Beijing have introduced a new, more accessible, and convenient method for enhancing images taken by ground-based telescopes using artificial intelligence. While various software methods have been used in recent years to improve the clarity of astronomical images, the new AI algorithm promises faster and higher quality results. This deep learning-based algorithm showed a 38.6% improvement in image quality compared to traditional deblurring methods. Although this may seem like a small difference at first glance, such improvements are of great significance for astronomy. Even minor enhancements in accuracy and efficiency can greatly expand the capabilities of cutting-edge astronomy. The team developed and trained the AI using data modeling the Vera C. Rubin Observatory, where the world's largest digital camera will be installed next year. The new algorithm will be compatible with the observatory immediately after its launch in Chile, allowing the latest technology to be used as effectively as possible to enhance astronomical observations. AI and ML play a crucial role in advancing space research, providing new tools and technologies for exploring space, analyzing astronomical data, and seeking answers to grand cosmological questions. In the future, they will continue to lead our journey to new horizons in the universe. Ultimately, the role of AI and ML in the search for the ninth planet is becoming increasingly significant. They not only accelerate the data analysis process, but also significantly increase the chances of successfully discovering this mysterious planet. Often, when mentioning the ninth planet of the solar system, the name Nibiru is brought up. It is claimed that scientists have already proven that this celestial body approaches our Sun every few thousand years, and something catastrophic happens at that time. Does the ninth planet, known as Nibiru, actually exist? Or is it merely a myth? What scientific research and discoveries might shed light on this mysterious question? In fact, Nibiru has never been a scientific hypothesis. There is a pseudo-scientific hypothesis that Nibiru is Planet X, whose elliptical orbit at perihelion crosses the solar system between Mars and Jupiter once every 3,600 years. This idea was invented in 1976 by American writer Zecharia Sitchin, 1920, who has no background in astronomy. He named it after the Sumerian Akkadian mythology. He also claimed that aliens known as Anunnaki by the Sumerians and Nephilim, or giants in the Bible, who entered world history as gods of various ancient cultures, came to Earth from there. Apart from Nibiru, various authors have proposed other information. For example, the gas giant Tyche in the Oort cloud. Astronomers John Matess and Daniel Whitmire from the University of Louisiana at Lafayette have repeatedly claimed to have evidence of a new planet based on the unusual behavior, periodic mass appearances in the inner solar system, of long-period comets. They noted that if Tyche exists, it should be detectable in the archive data collected by the WISE Space Telescope, launched on December 14, 2009. However, some astronomers have expressed skepticism about the existence of this object. In 2014, NASA reported that, according to preliminary data from the WISE telescope, the possibility of a giant planet the size of Saturn existing closer than 10,000 AU was ruled out, and a new planet the size of Jupiter could not exist closer than 26,000 AU from the Sun. The hypothesis of a ninth planet even extended to the brown or red dwarf Nemesis. According to a group of astronomers led by Professor John Matisse of the University of Louisiana, there could be another giant planet in the solar system, located about 2 light-years from Earth. Through detailed study of the orbits of icy comets, Matisse's group found that about 20% of comets entering the solar system are pulled by the gravitational forces of a massive cosmic object located beyond the Oort cloud, at least 1.4 times the size of Jupiter, but not a star. Otherwise, the percentage of comets captured by gravity would be much higher. According to scientists, some of these icy comets reach diameters of 2 kilometers and pose a potential threat to Earth. However, no astronomical evidence of their existence has ever been provided. The discovery or refutation of the existence of a ninth planet will have a significant impact on theories of planetary dynamics and the formation of planetary systems as a whole. This issue is not just about finding another planet in our solar system, but it is also a crucial test for modern astronomical models that aim to explain the complex processes occurring in space. If the ninth planet does exist, its discovery will help confirm theoretical models that suggest the presence of large celestial bodies beyond Neptune's orbit. This, in turn, will be important evidence supporting current views on the formation and evolution of the solar system, especially its outer regions. The presence of such a massive body could explain many unresolved issues related to the dynamics of trans-Neptunian objects, including their unusual orbits and anomalous spatial distribution. On the other hand, if the existence of the ninth planet is disproved, it will require a revision of several key theories in the field of planetary dynamics. In this case, scientists will need to seek alternative explanations for the observed anomalies. Regardless, such an outcome will also be of great importance for science, as it will open up new avenues for research and the revision of existing models. Furthermore, confirming its existence will have implications far beyond the solar system. It will open up the possibility of searching for similar objects in other star systems and potentially revising the criteria for finding exoplanets. In the long term, This could lead to a new understanding of the processes involved in the formation, evolution, and structure of planetary systems. This is particularly important for understanding the locations of habitable zones and conditions favorable for life in other parts of the galaxy. Thus, the question of the existence of the ninth planet extends beyond a narrow astronomical problem, becoming a significant aspect of planetary science and theoretical astronomy. Whatever the outcome of these searches, it will undoubtedly lead to a new phase in our understanding of the universe and its laws. This discovery could become a turning point in science, influencing the future of planetary science, astrophysics, and cosmology. Don't miss further events and discoveries. Subscribe to the channel and stay updated on the latest and most exciting achievements in the world of science.